Our topic today is sequences. Now, you all are pretty familiar with sequences to a certain extent, right? A sequence is just some ordered series of numbers, right? So we know a bunch of them. Here's a sequence of the even numbers, right? We can think of famous sequences like the Fibonacci sequence. Oh, well, I almost wrote 7, I need 8, right? Because I'm adding the previous 2 to get the next. All right, hello. Yes. Okay, anyway, so there's a Fibonacci sequence. We can also think about other ways of defining sequences. I mean, you can define them however you want, right? For example, I could do this sequence. This is just the nth digit is like the nth digit of pi, right? So a lot of these sequence, or you can have something that's just doing whatever, 1 minus 1. It's just going back and forth. You can just make up really whatever you want. And in fact, in our extra materials, there's actually a bunch of kind of fun or interesting sequences of integers, like all of these, of course, are sequences of integers that do really sort of amazing or interesting or fun things. So you can always go ahead and take a look at that, right? But not all sequences, of course, are sequences of integers. We could always have rational numbers or even irrational numbers, some very famous ones. We'll be looking at a lot of sequences that are fractions, right? So what would this be? This looks like 1 over 2 to the n, right? That's what this is. For example, okay, that's good enough, right? I probably have another one, but we can start with these. So if I want to write down, I already said something about, okay, how maybe we could give a formula for these, just sort of notationally speaking, what do we kind of tend to think about each of these as being a term, right? So, and we usually think of it as starting from 1. So the first term is A1, the second term is A2, etc. And because, because what it is, we tend to index it by n. So this sequence you could write as AN. Right? Sequences, we're interested in sequences that have an infinite number of numbers, right? So AN is good for all n natural numbers n. Sometimes we may start from 0, or sometimes we may start from 5, but for the most part, we try to start from 1. Okay, it's just a convention, so to speak. All right, and of course, once you have this, you can imagine very easily for some of these, like it's very easy to write down a formula here for the even numbers. AN is 2 to the n. For this one, this would just be -1. Okay, but if I do -1 to the n, it doesn't quite work for n equals 1, right? Because that would be negative. So I might want to put n plus 1 or n minus 1, whichever one is the same thing, right? Except I want to start from, yeah, it doesn't matter. So here, again, this would be like 1/2 to the n, but again, because I want to start from 1, maybe I want to put n minus 1. Definitely want to put n minus 1 in this case, right? Because I want n equals 2 to give me 1/2, right? So here, because I just have -1, okay, it doesn't matter if I do n plus 1 or n minus 1 to get this guy going backwards and forwards. It's just a question of either even and odd. But here, I have to make sure that n equals 1 corresponds to 1, n equals 2 corresponds to 1/2, etc. Okay, now Fibonacci, we had said what Fibonacci is, right? We said we just add the 2 previous numbers to the next one. So that formula looks a little bit different. So for Fibonacci, we start with 2 1s, right? So A1 is 1, A2 is 1, and then any other old AN, I just add the previous numbers. And I can write it this way. AN is AN minus 1, AN minus 2, right? So This is a formula of a different kind, right? Because instead of an being given explicitly in terms of n, it's kind of given in terms of the previous terms. So this is, when it's given in terms of n, we call that an explicit formula. And when it's defined in terms of the previous term or terms, this is called a recursive formula, right? Because you are looking at the previous terms. In fact, you can write down Fibonacci as an explicit formula. It's kind of ugly. It's not easy to remember in any way or shape or form. And many of the explicit ones, of course, you can also write down in a recursive way. If I wanted to look at this, I could also write this down that way. I'm just, because each one I'm adding 2 to the previous number, right? It's an arithmetic sequence. I'm adding 2 to the previous number. So I could just write A1 equals 2, AN equals 2 plus AN minus 1. Sorry, I don't have no space in here. Okay. This guy, of course, nth digit of pi, we don't have a formula for that at all. So if you wanted to write that down, you'd be sort of kind of out of luck. You could just write AN is the nth digit of pi. So fine. So that's going to happen too. And then especially if you look at some of those integer sequences in our extra materials section, there's these weird ones like the look and say sequence, or this other one which was jumping around, right? That have a rule that isn't easily written in terms of numbers, and that's fine, right? Because if you remember, okay, so let's go back a second. If you remember back in Calc 1 or even before that in pre-calc, they made this big thing about 4 ways to define a function, right? Well, sequences are in fact functions. You can think of them that way. They're functions whose domain is the natural numbers. So rather than the functions that we're used to drawing, where our domain is the real line, these are actually functions with the discrete domain. You only have basically a set of dots, an infinite set of dots, but a set of dots. And you can actually graph them that way as well. So here we see exactly that idea of 4 ways to define a function, right? It was numerically, so here, like a set of numbers. Algebraically, we can, in words, right? So these are the odd even numbers, right? So in words is easy. And then graphically, so let me show you, there's a nice little GeoGebra applet here, worksheet, where you can see, so all right, this isn't the one, let's look, whatever. What do we have? 2n, right? Something easy. All right, obviously. You can see what they have done then is here's n on the x-axis is n, and then your an is on your y-axis, and you can make this bigger. It's not very interesting here, right? Because it's 2n. Let's look at maybe something else. Also, none of these that I have on the board are really that interesting, right? Whoa. Except for perhaps Fibonacci. Okay, why is it doing that to me right now? It wasn't doing that before. I don't know what's going on here. Okay, there we go. I don't know what that was about. Okay, so here's our other one that we had down here. Oh, 1/2 to the n. Okay, I should put it n minus 1, so it starts from 1 like we wanted. But again, you can see what happens here. They're getting very, very small, right? So this is exactly what we expect. We see that like an exponential, right? Because this is an exponential. If I instead did 2 to the n, it would get very big, right? Very big, very fast. So this is going up here. You can see how big the scale is. You can see if I just go down to a few n's, you can see it goes up very fast, like you would expect 2 to the n. or to the n minus 1 is going to do. Okay. So, but what's interesting here, sort of thinking about these as sequences, as graphs, right? So if I do my num minus 1 to the n, okay, we can see you're bouncing back and forth between -1 and 1. Okay. We can start thinking about, and then as I go further, I can do, it's not going to change, right? It's going to do the same thing. It's going to bounce back and forth. So what I can do further is I can start thinking about, well, you can see where we want to go with this. Just like with regular functions, we were looking at, okay, what's going to happen in the limit as n goes to infinity, as x goes to infinity. It's the same thing with these sequences. What's going to happen in the sequence as n goes to infinity? So now we're going to start looking at sort of that idea of the limit. So that's what they have here. Enter sequence, where do the terms seem to be headed? What did we have before? We had like n plus 1 over n plus 2. Okay, you can see that that's going to head to 1. Of course, x plus 1 over x plus 2 would head to 1 as well if you had this as a function of x as a continuous function, right? That's not really surprising. Interesting things we can do with this discrete behavior, though, is let's say we can put in, let's see if I can do it so it'll let me do it. Sometimes there's this minus 1 to the n. Now, here I got minus 1 to the n. We'll do it. It does. Yeah, it did it. It did it. No, it didn't do it. It didn't understand what I wanted. Okay. It's not understanding what I want. Okay, I want this. It won't do it. Come on, babe. All right, so having a little bit of technical difficulties here. Unsurprised. Come on, man. Don't do this to me. All right, here. Maybe if I just put this in there. Will it do it now? Ah, there it is now. Okay, and then it gives me back exactly what I was trying to write in the first place. But anyway, so what this is, if I look at this, okay. If I look at the numbers, it might make a little more sense. So when I had an being n plus 1 over n plus 2, you can see what these numbers are, right? I'm starting with 1, so I'm starting with 2/3, then 3/4, 4/5, 5/6. And when we graph these numbers, it really does look like they're going to 1, right? But now what happens if I put in that minus 1 to the n? All I'm doing is I'm making these numbers change sign, right? So I start with minus 2/3, but then the even ones are always going to be positive. Minus 6, 7, etc., right? So though this one, as we saw, will converge to 1, this one is not approaching 1. Part of the numbers are approaching 1, but the other part of the numbers are approaching -1. So this one, I can take the limit, and I can take the limit just the ordinary way, right? I can do limit as n goes to infinity of n plus 1 over n plus 2, and same way as we did a million times in Calc 1, right? Multiply top and bottom by the highest power, and then you have limit as n goes to infinity of 1 plus 1 over n, and 1 plus 2 over n. These go to 0, and I end up with 1, right? So we can show immediately that this one goes to 1. This one, though, I've got that minus 1 to the n there. That's not something that we've seen before because it doesn't make sense to say minus 1 to the x, right? Like, what if x is 1/2? It's not defined. So I can't use a minus 1 to the x. But I can certainly use a minus 1 to the n here because n is just a natural number. So you get a different behavior sometimes that you can look at with these kind of series, the sequences. My bad, I apologize. Let me show you again what I'm getting at. So if you look at that here, you'll see those are all the positive ones. The positive ones, of course, are going to 1. And then negative terms are then, of course, approaching -1 because all the -1 to the n does is it changes the sign. The numbers, as we saw, are still the same numbers. Okay, so there's sort of interesting behavior here that you can see that we can talk about more when we're talking about sort of what does the sequence do, where does it go? And then there's lots of, it doesn't have to just be, for example, an algebraic thing like I had up there. We could say do cosine of n. Let's do cosine of n. All right, cosine of n. Now think about what that's really going to look like. N is just cosine of 1, cosine of 2, cosine of 3. Those are like not like weird numbers, right? Because what is like 4 radians anyway? So this is what you're going to get. You're going to get something for cosine of n. Yes, that's all defined, but there's like not really a discernible pattern. And certainly if I talk about is this going anywhere, is it approaching any number as n goes to infinity? Well, of course it's not. It's just all these weird numbers between -1 and 1, right? Now, I might want to do, for example, something like cosine n pi over 2. I had that working before. Cosine n pi over 2. Okay, see, it does know that. And this now makes a little more sense, right? Because when n is even, this is going to be plus or minus 1, so you see some plus 1s and minus 1s. But when n is odd, if I think about going around my unit circle, all those odd ones are going to be 0. So here you can kind of see that, all right, some of my terms are headed towards 1, some of my terms are headed towards -1, some of my terms are headed towards 0. Obviously, the sequence itself is not going anywhere, right? Because it's still bouncing all around. If I make it n pi, of course, I'm not going to have the zeros. I'm just going to have the -1s and 1s. If I make it 2n pi, oh, no, thank you. Would you stop? Or if I make it 2n pi, then they're all 1, right? So now this sequence is convergent because this sequence is always 1. It's always going to stay 1. So it's basically the sequence that's all 1s. So we can play with a lot of this kind of stuff.